Henry Frohlan from University of Washington will tell us about measuring entanglement of non-Gaussian states.
Hi, I'm Henry Frohlan at the Incubator for Quantum Simulation at the University of Washington, and today I'm going to talk about measuring entanglement in non-Gaussian states. So we're all interested in quantum simulation, and one of the key applications of current quantum simulators is studying the real-time dynamics of quantum systems. And in particular, studying thermalization, or how these systems reach equilibrium after you evolve them for some time. There's many different ways to define thermalization, and in this talk, we're going to be focusing on two pictures. The first comes from thinking about correlations. So I can take some observable, evolve it in time, and watch it reach its thermal expectation. And this is, you can call that thermalization, and this is a very nice picture because it's experimentally accessible. However, if you kind of want to understand the deeper mechanisms of thermalization, you can look at the state, and in particular, the entanglement of the state. This gives you kind of a nice understanding about what's happening, but it can be really tricky to extract entanglement in a lot of situations. And so we want to think about how can we combine these two pictures? How can we combine correlations and entanglement? So the setting will be a 1D Fermi-Hubbard model with interaction strength controlled by U. For the rest of this talk, we'll consider U to be very small compared to the timescales considered. But first, let's consider U equals 0. In this case, the dynamics are described by Gaussian states, which are completely characterized by their two-point correlation function. In fact, I can explicitly write out a Gaussian state in terms of its two-point function. And so this is very nice, because if the physics you want to study is contained in the two-point functions, then the Gaussian states provide a very flexible toolkit that allows you to study dynamics. However, if the physics is contained in higher order non-Gaussian correlations, then you kind of have to push the Gaussian state formalism further. And this is what we're going to be doing. Before we do that, let me also talk about entanglement. So we have a system. We can consider a subsystem, which I'll call A, and you can define a reduced state on that subsystem. If you take the log of this, you get something called the entanglement Hamiltonian, which has all the same information as a reduced state, but often has a very nice structure. Part of this structure is in its spectrum, which, surprise, surprise, is called the entanglement spectrum. The entanglement spectrum encodes information about how a system thermalizes. And you can see this by looking at level repulsion. Level repulsion basically tells you how correlated the different levels in your spectrum are, or how close they want to be together. And you can quantify this by looking at the gap ratio. So if you consider adjacent levels in your spectrum right there, and you consider the gaps between them, you can form this ratio and look at the distribution of that ratio over the entire spectrum. For a system that doesn't thermalize, this distribution will be Poisson. And it's important to note that this Poisson distribution is peaked at r equals 0, which means that in this case, your levels are really happy to sit right on top of one another. For a thermalizing system, you'll see Gaussian unitary statistics. And importantly, this distribution is very close to 0 at r equals 0, which means that on average, your levels want to be far away from one another. Because there's correlations induced by the dynamics. An important point to note is that for Gaussian states, you will never see level repulsion. And so that means to study level repulsion, you really need to start pushing beyond the Gaussian state formalism and include non-Gaussian correlations. So to do this, we're now going to turn on U, still very small, and subsequently generate these non-Gaussian correlations. And so now that we have these non-Gaussian correlations, we want to figure out how we can incorporate these into the state. And essentially find an approximation of our state that depends on our two-point functions and our non-Gaussian correlations. Since U is small, higher order non-Gaussian correlations will be suppressed in powers of U. And so for the purpose of this talk, we'll consider the leading order non-Gaussianity to be contained in the four-point function. So to approximate the state, well, we have two-point functions, and we have the Gaussian parameterization, so we can consider that as kind of the 0th order in approximation. And then to include four-point functions, we're going to add on this little delta rho piece. Is that working? We're going to add on this little delta rho piece, which you can consider as a non-Gaussian perturbation on top of our Gaussian state. And we're going to put these together, and we'll call it rho tilde, which is essentially a parameterization, or you can think of it as an ansatz, kind of the non-Gaussian analogy for the Gaussian state expression I showed you. And this is how we're going to try to study thermalization dynamics. It's important to note that this ansatz is still much lower complexity than the exact state, as we've thrown out, essentially, an infinite number of non-Gaussian correlations. Before we jump to thermalization, let's first study how well this ansatz actually reproduces, aspects of the state. So the first thing we looked at is how non-Gaussianity builds up. And we did this using this measure of non-Gaussianity theta, which essentially you can think of as the distance between a state, or the fidelity between a state and its Gaussian version. So the setup here is that you take your initial state to be Gaussian, you turn on interactions, and you watch non-Gaussianity slowly build up. On the far left, we have the exact state and the exact buildup of non-Gaussianities, and right next to that is our ansatz. And as you can see, in early times, you effectively get this linear ramp exactly. The ansatz, rho tilde, it doesn't go quite as high, which makes sense because we've thrown away a lot of non-Gaussian correlations. But qualitatively, you get it essentially exactly, and you also get a lot of quantitative features. Since we're ultimately interested in approximating the entanglement spectrum, we also looked at the spectral error, which you can essentially consider to be the difference between the exact answer, which is this epsilon sub a, and whatever you're using, your approximation is. So you can look at the Gaussian approximation and our ansatz. For the Gaussian approximation, since this doesn't contain any information about interaction, you expect this to fall off at order u. Our ansatz, however, since we claim to have captured the leading order effects of the interaction, you expect this to fall off at order u squared. And this is exactly what you see. So these purple lines correspond to the Gaussian approximation, and the pink lines correspond to our ansatz. And this is for many different initial states. And as you crank down the coupling, you see this really nice separation that has the exact scalings we predicted. So this gives us a lot of confidence that this technique, this method, is going to be really accurate in capturing, a lot of aspects of the state. Now the question is it good enough to get thermalization? The answer is yes. So if you look at this plot on the far right, this is showing the buildup of the gap ratio over time when you quench from an initial Gaussian state. So it starts at the Poisson value, and over time it reaches the GUE value. This gold line is the exact gap ratio, whereas the purple is our ansatz. And as you can see, kind of at intermediate times, it's a bit below, but for the most part, it gets the timescales bang on. And so as you can see, this ansatz, despite being very low complexity, has enough expressive power to really capture thermalization. You can ask what happens over a larger range of interaction strengths. These are these plots on the left. The top is the exact, the bottom is our ansatz. And as you can see, going from blue to yellow, Poisson to GUE, no level repulsion to level repulsion, again, our ansatz gets this crossover up to very small quantitative fluctuations. It gets it very exactly. And so this is great because now we have a very low complexity way to study thermalization. So you might ask yourself, how is this useful? Well, so we've envisioned a number of applications of this. The first and foremost is actually using this in experiment to study thermalization in the lab. And in particular, we consider this for neutral atom devices that can naturally implement a Hubbard model. In this case, measuring entanglement can be very tricky, but measuring correlations is easy. You can literally just take snapshots of your system, do some post-processing, and then plug them into this ansatz, and there you have it. You're immediately seeing thermalization. So with that, I've given you a parameterization of a quantum state that's low complexity. It scales polynomially with subsystem size. It still has the expressive power to resolve the fine structure of entanglement as encoded by the entanglement spectrum, and it can capture the timescales of thermalization that are otherwise very hard to extract. And It has applications to both experiment and theory, and it can be extended to all orders. I didn't show this, but we've shown how you can basically include any type of correlation you want, any non-Gaussian correlation. With that, I would like to thank my collaborators, Nicholas Mueller, Robert Ott, and Torsten Zache, and I'd like to open up for questions.